Hey everybody, it's Sakai Weather here, and today we are going to be talking about one of the most important new theories in synoptic severe weather meteorology, more specifically, the nudger theory, which seems to play a very big role in tornadogenesis. But when it comes to nudger theory, when it comes to understanding nudger theory, first we need to go back to basics. We need to go back to the supercell thunderstorm. More importantly, we need to understand where in a supercell is air rising and where in a supercell is air sinking. Those concepts are incredibly important to understanding nudger theory and tornadogenesis in general. So first of all, obviously the most interesting part of the supercell is the hook echo right here. You can see that our tornado right here, that debris ball, our tornado is always associated with what we call a mesocyclone, a rotating updraft column of air within that supercell. The mesocyclone is an updraft, which means that air within the mesocyclone is being forced upwards. Here, air is rising. However, that's not the case for all over the supercell. Here, this air part of the supercell, which is going out and forward ahead of our mesocyclone and our tornado, is the forward flank downdraft. Here, precipitation that forms higher up in the storm is falling back towards Earth. So here, you have a consistent downward movement of air in this area, the forward flank downdraft. Additionally, here, although you can't see it on radar, we have another downdraft, which is called the rear flank downdraft. The rear flank downdraft forms from behind the supercell when dry air in the mid-level suddenly sinks to the surface, and it plays a very, very important role in tornadogenesis. The rear flank downdraft can sometimes be seen on radar, as even though it has dry origins, it can also bring precipitation with it. Usually, when an RFD begins to kick into gear and begins to work on increasing tornadogenesis potential, you will see precipitation fall downwards from the storm, being brought there by the RFD, and curl up around the hook echo, which gives the appearance that precipitation is curling inwards into our hook. That is a downdraft. So here, the mesocyclone is the key updraft. The rear flank downdraft and the forward flank downdraft play a very important role in tornadogenesis. But how does that apply to nudger theory? Now that we know the basics, let's go to a famous case of the nudger theory in action. June 13th, 2001 produced one of the most famous tornadoes in Nebraska history, which was a beautiful F4 that formed near the town of Seward. This is about 30 to 40 minutes before tornadogenesis. Here you can see we have a line of storms here. Most of these storms are in a line, they're pretty linear. These storms up here are dealing with a lot of unfavorable mergers. You can see this supercell is being shunted by inflow from supercells to its south. This one has a lot of dry inflow into it. This one has a lot of, really isn't surging at all. And this one is being cut off by this massive storm to its south. This supercell is really the only one that's open. But how does nudger theory work? The basic principle of nudger theory is that you will have another storm come in and hit the supercell of interest from either the southwestern flank or the western flank. Why is that important? Take a look here. You can see these storms go up here. These new storms go up, and they hit the supercell at the southwest. The first storm hits the supercell, and after which you can see rotation noticeably increase. Here, between these scans, the first storm hits the supercell. You can see rotation increase, and then it increases some more. But then, as the second storm hits, that rotation suddenly dies. But as that second storm merges with the original storm, and the inflow clears, you will see the tornado rapidly take shape. And there's our tornado. But why does this work? Remember, go back to our picture from earlier. Here is the forward flank downdraft of the supercell thunderstorm. The forward flank downdraft is always present from very on within a storm's life. So you can see these storms here, they have forward flank downdrafts. You will remember that a mesocyclone is an updraft, and it needs air to go up in order for it to thrive. However, one way to improve the speed of wind and the quality of wind, the magnitude of wind going into the updraft, is to put a downdraft right next to it. Air will always flow from a downdraft towards an updraft, or will flow from an area of high pressure, which would be like downdraft where air sinks, to an area of low pressure, which is what an updraft would be. Air rises in low pressure, air sinks in high pressure, air will flow from high to low pressure. So, you can see how the forward flank downdraft of this storm appears. You can see that the forward flank downdraft of this storm is right next to the hook echo of our main supercell. that means that you're putting a downdraft right next to this updraft. All of a sudden you have a low pressure system and you put a high pressure system right next to it. Air that's sinking in that high pressure system is going to flow directly into that region of low pressure, thus significantly increasing the winds that are going from that high pressure system to that low pressure system. That change right there is the basis of nudger theory. When you put a downdraft right next to an updraft, that increases inflow into that updraft, and it can increase just enough to result in tornadogenesis. And this is a process we have seen documented extensively. Here, you'll see it happens. But you may ask, why? This first storm merged with this supercell. Why did it suddenly stop producing a tornado? Why didn't it suddenly stop? Why didn't this first merger produce a tornado? Well, as you can see here, some of that first merger's inflow kind of began to clutter the inflow region. One important part about nudger theory is that it storms from the southwest or the west, or storms that tend to hit the parent supercell at an angle to where it does not affect the inflow into the mesocyclone. Because if a storm were to crash into a supercell from the south, which was the case with this one right here, that means that stable air from the FFD, because air that sinks is air that's stable. Sinking air from the FFD, if it's in the inflow region and enters into the inflow region of the supercell, will introduce stable air into the mesocyclone and it will kill it. That's what happened here. You can see a little bit of that first storm got into the inflow region right here, put stable air there, killed that mesocyclone quickly. But the second storm, as the second storm came, you can see the inflow region clear. And the forward flank downdraft of that second storm did not affect the inflow region until way after the tornado had already formed. And only after the tornado formed do you see the FFD of that second storm begin to protrude and choke that inflow region, and that quickly resulted in the tornado dying, as you can see here. That is the basis of nudger theory. Let's look at another example. April 5th, 2022, some of you guys may recognize this as the Pembroke tornado. Now, this was about less than 30 minutes before tornadogenesis. Does it look impressive? No, it does not. But let's see what happens. You'll see we have our main supercell here, and then we have the FFD of another storm come in crashing from the south. Obviously, it begins to choke off the inflow into that developing supercell, not much happens there. But then, as that merger occurs, you will suddenly see a hook echo appendage appear here very, very rapidly. And all of a sudden, sometimes another way in which nudger theory can work is if you have a new supercell come from the southwest, it doesn't have to hit the original supercell perfectly at an angle to put that downdraft right next to the updraft. Studies have shown that when two supercells emerge, especially in the developing stage of a supercell, they can dramatically intensify and become one combined supercell and significantly enhance the updraft potential and just the overall strength of the updraft within the supercell. And that will give you a very healthy storm in an environment right here. And then you'll see also, as those storms intensify, another particle begins to affect this storm from the south. You can see a little shower go up right here. You can see that kind of dog-leg feature with that small shower right to the southwest of that hook echo to help with another downdraft. And so that merger caused that supercell to rapidly intensify. We have some trailing convection here that is kind of hanging onto the hook echo and providing more and more of a downdraft. And as you can see, the tornado rapidly intensifies. Now let's see. Why does the tornado dissipate? Well, if you'll notice here, you see a convection. Some new convection goes up right here. And you can see where that convection went up. That convection went up into the inflow region and began to introduce stable air into the mesocyclone. The tornado dissipated, and stable air just kept on going up ahead of the supercell, and it was really never able to produce another tornado because stable air kept on going up in the supercell's mesocyclone area, and it kept throwing stable air into the inflow, thus preventing this storm from producing another tornado, apart from the time where it first had that favorable merger, right here, favorable merger, and then you had some convection go up right at the perfect spot southwest of the hook echo, in a position where it would put the downdraft right next to the mesocyclone updraft without throwing stable air into the inflow region. And now let's look at arguably the most famous case of this that I could find. I wonder what day this is. May 3rd, 1999, one of the most famous supercells in history. Let's look here. Here, not much sort of stuff going on tornadically, but look here. There's some convection coming from the southwest. And as that convection comes from the southwest, it puts that downdraft right next to that mesocyclone updraft, increases the wind flow into that updraft, and you quickly get tornadogenesis. You can see as convection just continues to stay there, put that downdraft right next to that updraft, the tornado becomes extremely, extremely strong. And after this, it actually weakened a bit as that convection that was putting that downdraft next to the updraft kind of went away. But then it got some more convection as it went into more, heavily re-intensified, and became one of the most catastrophic tornadoes in history. Thank you for listening to this talk on nudger theory, and I hope that this video helps you understand nudger theory better. Thank you for watching.